since you began studying physics a few weeks ago, you've been engaged in measuring things. Measurement, after all, is the heart of science. You've made measurements yourself, and you've seen professional physicists make measurements. Up to now, though, you've been primarily interested in what you were measuring. Today, we're going to concentrate instead on the hows and whys of measurements itself. As an illustration, we're going to perform a particular measurement. We're going to measure the speed of a bullet as it leaves the muzzle of this rifle. Why did I choose this particular experiment? Well, for two reasons. In the first place, nobody, except possibly a specialist, is very much concerned about just exactly how fast a bullet goes. So we can worry about what we're doing and not have to be much concerned with how it comes out. In the second place, this experiment is just complex enough to bring out most of the things that are important in any measurement. And yet, it's basically simple. We're going to measure the time it takes a bullet to go a certain distance. Now, it's obvious, I think, that we can't use an ordinary watch to time the flight of a bullet. So we'll use this electronic watch instead. To start and stop our electronic watch, we have these two electric eyes. When an object interrupts this light beam here, it starts our watch going. And when it interrupts this second light beam, our watch will stop. The balance wheel of our electronic watch is this oscillator, which puts out electrical pulses, ticks, at a rate of 100,000 per second. The manufacturer of this oscillator, by careful attention to design and calibration, is able to guarantee that the frequency of the oscillator will be exactly 100,000 per second to the order of 2 parts in a million. And that's a pretty impressive claim. We can indicate this accuracy by writing a certain number of digits. 6 in this case, called the significant figure. And then we can add on another number, plus or minus 0.2 cycles per second, to indicate the expected deviation. Does it bother you that you don't know exactly how this electronic watch works? But do you really have to know how it works? No, not really. Not for the purposes of today's experiment, at least. You probably don't know exactly how this works either, but that doesn't prevent you from using it. We often use an instrument or device in this way without stopping to analyze the details of its working. And this is perfectly proper, provided that we make certain that it behaves the way we want it to. Physicists sometimes call an instrument used in this way a black box. This concept of the black box is an extremely useful and important one. Of course, physicists are often interested in what goes on inside black boxes. But when you take the lid off, you usually find still more black boxes. And indeed, you can go on finding smaller and smaller black boxes inside black boxes until you get down to the subatomic particles themselves, and they're the blackest black boxes of all. But if we're going to use an instrument as a black box, then we should be careful to check its performance, see that it behaves the way we want it to. So let's check our electronic watch. Now, this motor runs at 1,800 revolutions per minute. Now, the speed of a motor of this type depends primarily on the electrical power line frequency, and we know that that's carefully controlled because our electric clocks are regulated by it, and they keep good time. So let's see if our electronic timing device can measure the speed of the motor's spin. First, I'll reset our clock to 0. Now, after I push this button, the first time that the longer arm on the motor cuts through the light beam, it will start our watch. And the next time that it comes around, it will stop the watch. And from the time interval between, we can determine the motor's speed. This black box here counts the ticks coming out of the oscillator. It's like the face on a mechanical clock. It reads 3331. Let's do it again. First, I'll reset the watch and push the button. You'll notice that each time the count is nearly the same, except for the last digit. Furthermore, the counter read 3331. But since each count is 100,000th of a second, or 10 to the minus 5 seconds, the actual time was 0.03331 seconds. Now, the motor made one revolution in 0.03331 seconds, which is approximately 30 revolutions per second, or multiplying by 60 to give revolutions per minute, is just what the manufacturer stated. So we've tested our black box and seen how it behaves, if not exactly why. But I think we feel much more confident about using it to measure the speed of the bullet. Now, our measurement of speed is what is called an indirect measurement. We get the quantity we want, speed, from a calculation involving two other measurements, time and distance. To use our electronic watch, all we have to do is to put our electric eyes at the beginning and at the end of the measured distance. But how long should this distance be? And how far from the muzzle of the rifle should it begin? These are important questions with respect to our experiment, and we'll have to consider them carefully. In the first place, the longer the distance within reason, the more precise our measurements of both distance and time will become. Take the time measurement, for example. Our counter can't count fractions of a tick. So the greater the total number of ticks, the less relatively a fraction of a tick matters. And as we'll see, exactly the same sort of condition applies to the distance measurement. On the other hand, because of air resistance, our bullet will slow down. And the greater the distance between our electric eyes, the more important that effect will become. So some sort of compromise is needed. And a compromise is also necessary between our desire to get as close as possible to the muzzle of the rifle in order to measure the muzzle velocity accurately, and on the other hand, the necessity of being far enough away so as to minimize blast effects. How should these compromises be resolved? Well, we can't say in general. It depends on the purpose for which our measurement is intended. And frankly, in the present case, we've selected the distances you see primarily for convenience. But notice that in trying to carry out our measurement, we found that we had to think more carefully about what we were measuring. This is a common occurrence in science. In trying to answer a question, you often find that the question itself was not exact enough, or not complete enough, and you must come back again and again to rephrase it. Next, let's measure the distance between our electric eyes. We will measure this distance directly, that is, by comparison with a steel tape. The tape, in turn, has been calibrated by comparison with a standard. And indeed, every distance measurement eventually is a comparison with some standard, such as the standard meter in Paris. The distance is 1.486 meters. But let's examine this familiar measurement more closely. In a sense, what we've done is to select an answer from a set of possible answers. We knew before we began that the distance had to be somewhere on our tape. All we had to do was to decide where. And our decision is represented by a number with 4 digits. And each digit in itself represents a decision on successively finer scales. For example, the 1 represents our decision that the answer lies between 1 and 2 meters. The 4 that it lies between 1.4 and 1.5 meters, and so on. Any direct measurement, no matter how complex, can be broken down into a similar series of yes or no decisions. The number of decisions, together with the number of alternatives from which they were selected, can be thought of as essentially measuring measure. Now note that I wrote the distance as 1.486 meters, not as 1.486000 or as 1.486293. By writing just this number of figures, the significant figures, I show that I am reasonably certain of the value and meaning of these digits, but have no idea of what the succeeding digits should be. Now, measuring the distance to the nearest millimeter doesn't mean that I'm lazy. The light beams entering into our electric eyes are on the order of a millimeter in thickness, and they have fuzzy edges. So it could be very difficult to attach much meaning to distance measurement accuracy that was greater than a millimeter. It's important to realize that every measurement has certain built-in limiting factors which largely determine how accurately that measurement can be made. We human beings have limiting factors built into us, too. For example, we could never count the electrical pulses coming out of this oscillator at 100,000 per second. And human senses aren't very well adapted for electrical pulses anyway. So we have this counter to count the pulses coming out of our oscillator and to convert them into these lighted figures which can easily be read off. Well, I guess we're about ready to pull the trigger. We have a pair of electric eyes at the beginning and end of our interval to start and stop our counter. We have a source of time ticks fast enough to handle the bullet's speed. And we have a counter to convert our oscillator's ticks into a signal we can use. Ready? Here we go. Now let's see what our time measurement was. The counter reads 0495. But each count is 100,000th of a second, so the time really is 0.00495 seconds. Now we have both a time and a distance measurement, so we can compute the speed. This doesn't do anything I can't do, but it's faster. Let's see, the answer is 300.202. But the original data from which this was computed was only known to a certain accuracy, so these additional digits came in when we divided our original numbers. They are not really a result of our measurement, and they have no physical significance, so I'll just erase them, leaving 300 meters per second. So we have a measurement, but what do we really measure? Does our answer represent something that really happened in this world, or is it just a meaningless mathematical scribble? Well, one way of checking the significance of a measurement is to try and repeat it and see if you get the same answer. This time the counter read 0549. Which gives for the velocity 271 meters per second. A different result. Now, I've run this experiment a number of times, and some of the results I got are shown here. Far from being the same, the answers are all different. Before we can call our experiment completed, we must try to find out what could have caused these fluctuations. One possibility is that in either our distance or our time measurement, we introduced an error that fluctuated considerably from experiment to experiment. For example, you remember the difficulty introduced in the distance measurement by the width and fuzziness of the light beams. Possibly each time that I read my tape, I read it in a slightly different way. But it's hard to see how the error introduced in this way would be much greater than about 1 millimeter. And that might affect the last digit of our speed calculation, but not the others. The observed differences are much greater than that. So the random differences, or noise as it is sometimes called, introduced in this way, can at most account for a small part of the observed variation. Well, perhaps it's our electronic stopwatch that's giving us trouble. But you recall that we tested this several times, and it behaved quite consistently, except possibly for the last digit again. So random errors or noise in the time measurement can account for only a small part of the differences. We must conclude, then, that the quantity being measured, the speed of the bullets themselves, varies from bullet to bullet. This is understandable and easily explained as a result of slight variations in the weight of the bullets or in the amount and burning rate of the charge. But in every measurement, it's important to determine whether the principal source of the fluctuations is in the measuring equipment or in the quantity being measured itself. Both types of situations occur in physics. For example, if we were interested in measuring the force of gravity in this room, it would probably be reasonable to assume that any fluctuations in gravity would be so small and so slow, from measurement to measurement, that any apparent changes that we observed would most likely be due to random noise errors in our measuring equipment, and not to changes in the force of gravity itself. But the situation is quite different if, as in our experiment today, where we used a number of different bullets, the quantity being measured itself fluctuates from experiment to experiment. There is no one single number which represents the precise speed of all the bullets in the box. Of course, we can determine the precise speed of one particular bullet, but only after it has been fired. For some purposes, this might be good enough. But suppose that we were interested in predicting as accurately as possible the muzzle velocity of a bullet before it was fired. Well, probably the best thing to do then would be to present all the data that we have, either in the form of a table such as this, or as a bar graph or distribution chart. If that's too much data, it's confusing, then we might settle for the average value as being the most likely estimate of the speed of a bullet before it's fired. And together with the average, we might include a measure of the spread in the distribution to suggest how large a deviation is likely. And this is the way an average and a spread are usually written. Finally, there is one other kind of error whose presence must be suspected in every measurement, which is not made apparent by repeating the experiment. This is called bias. Bias is perhaps best explained in terms of examples. Suppose, for example, that our steel tape had been incorrectly calibrated. Or suppose that, unbeknownst to us, our oscillator were putting out only 95,000 pulses per second instead of 100,000 as we assumed. Our answers would then all be in error, but all in the same way. So this error would not show up when we repeated the experiment. Bias can also be caused by an interaction between the quantity being measured and the measuring equipment. Now, it's hard to see how a light beam can have much influence on a bullet. But suppose that we had used a wooden shaft instead. I think you'll agree then that the bullet would have been slowed down a good deal by hitting the shaft. In our present experiment, there is one other source of bias that we've already talked about. If we are interested in measuring the muzzle velocity of the bullet, then our answers are all too slow as a result of air resistance and the large distances required by our measuring method. Probably, though, these errors are small in comparison with the fluctuations in speed from bullet to bullet, and perhaps they can even be ignored compared with the small noise errors in our time and distance measurement. Well, we've made a fairly complex measurement and seen that it involves many things. But don't get the idea that these processes of measurement are restricted to fancy electronic equipment. In fact, measurements is, as much as anything, an attitude, a frame of mind. and the equipment is just secondary. It's the way you approach a measurement that is important. The answer you get is no better than the question that you ask. And this is true whether you are measuring the distance between your school and your home, or whether you're performing a complex experiment in the laboratory. Indeed, when you get right down to it, what we've been trying to show you today is how to ask the right question.
Pacing was one of the earliest methods of measuring distances and is still in use today. But for thousands of years, men have been able to calculate distances without directly measuring them. Probably the Egyptians first discovered the method of triangulation, which is the basis of surveying. These men are laying out a baseline with a steel tape, the first step in measuring the distance to a point across the river. Into the top of a heavy wooden surveyor's stake, a spatial nail or pin is driven to mark the end of the baseline precisely. Then, with the tape pulled tight, the length of the baseline is accurately measured. The transit is placed precisely over one end point. The exact position of the other end of the distance to be measured is marked. Then the surveyor carefully measures the angle between this objective and the baseline. The surveyor's helper makes an accurate record of all data. Similarly, at the other end of the baseline, the surveyor again measures the angle between the objective and the baseline. Thus, he knows the length of the base and two angles of the triangle. And, as you have learned, with two angles and the baseline known, you can find the distance to the objective. Here is a station for tracking artificial satellites, where a more complicated system of triangulation, using radio signals, measures the distance between the satellite and the station. And this type of rangefinder, which you can make for yourself in the physics lab, is also based on the method of triangulation. Maps are based on the triangles made by many surveyors as they work around the country. Notice in this particular one, the very large number of triangles that have been used to establish a small number of accurate points, around which then the other points can be determined less precisely. Over the United States, we have an enormous grid of interlocking triangles that have been developed by the surveyors over many years, and each of these points is very precisely determined with a lot of work. And this gives us then the basic triangulation grid covering the whole country. Each point is marked by a survey marker, a brass marker, such as the one we have here from the U.S. Coast and Geodetic Survey. It's put in the ground or into cement or rock. Notice here the little dimple in the middle, and that is the point to which the surveyor returns if he ever needs to use that position again. There's a $250 fine for moving one of these, so leave them alone if you find them. Until recently, it seemed that surveying would be the only way by which we could be able to make maps. But recently, aerial photographs, such as this one of San Francisco, have been used to make maps like this and of many other areas of the country. In any such map, it's necessary, however, that we have 3 known points so that we can determine the north-south line and the scale of the picture so it can be put together with others that would cover a very large area. In the future, it's rather probable we'll be able to make maps of even larger areas by using photographs such as this, taken from the tail of a high-altitude rocket fired from White Sands, New Mexico. From here, 140 miles up, you can see all the way from Texas to the Pacific Ocean. Nowadays, geophysicists, the scientists who specialize in the study of the Earth, are using artificial satellites to determine more accurately the size and shape of the Earth. But the old Greeks, many years ago, had techniques which were very good, and you can use yourself to determine the size and shape of the Earth. Aristophanes learned that in the middle of June, at noonday, the sun shone directly down a deep well in the city of Cyrene, near the modern town of Aswan. Almost due north of Cyrene, in the city of Alexandria, he knew from the length of the shadows that on the same day, the sun never passed closer than 7.5 degrees to straight overhead. If the Earth were round, the sun's rays at Cyrene would point directly along a radius of the Earth. But the parallel sun's rays at Alexandria are 7.5 degrees off the radius. Therefore, 7.5 degrees would be the angle at the center of the Earth. And as a result, if he could measure the distance between the two cities, he could measure the size of the Earth, which would be 48 times this arc between the two cities. He did make this measurement and was able to obtain a very good figure for the size of the Earth. Now let's take the Earth and put it out in space. Down there, we have a scale model of the moon, made to just the same scale as the Earth itself. Now we're going to see how, by triangulation, we can measure the distance between the Earth and the distant moon. In any triangulation, it's very important that we have as long a baseline as possible. Particularly in astronomy, where the distances to be measured are very great, we need a long as baseline as possible to increase the accuracy of our results. Now, to get the distance to the moon, let us ask an observer in Stockholm, Sweden, to observe the moon and compare it with observations of one from Cape Town in South Africa. We will ask our observer in Stockholm, whose distance from Cape Town we know, because we've measured the size of the Earth, to point his telescope at a particular point on the moon. And then we shall ask the observer in South Africa to do the same. As seen from Stockholm and South Africa, the angle displacement of the moon in the sky would be a little less than 2 degrees. If we could actually get at the North Pole and the South Pole, we would find that the moon was shifted 2 degrees in the sky. Now, that may not sound like very much, but it's quite a large amount in the sky. To give you some idea of that, we find that a dime held out at arm's length will cover the moon rather nicely. If we were to observe from the North Pole and the South Pole, you would find that in the sky, the position of the moon was shifted about 3 dimes worth up in the sky. From many observations of this type, we know that the average distance between the Earth and the moon is 380,000 kilometers. Now, that's such a large distance that it makes no sense to you or to me. We're accustomed to working with feet or possibly miles. To help you visualize this enormous distance, we've brought together here a model of the Earth and of the moon to scale. The moon is to scale and placed 30 times the Earth's diameter away from the Earth. It's possible with radar to measure the distance between the Earth and the moon, but not with as great precision as we can obtain using the trusted and experienced methods of triangulation. Let's have a look at the sun. When we attempt to measure the distance of the sun by triangulation, we find that it's almost an impossible task. You remember that we had to sight on a particular spot on the moon to make our measurement. However, as you can see, there are no permanent markings on the sun. How would you go about determining the distance to the sun? There are some ideas about this in the film notes. The distance to the sun has been measured many times by many different means. The results always come out about the same. 150 million kilometers. And the diameter of the sun comes out to be over 1 million kilometers. To get some idea as to what 1 million kilometers is, here's another view of the sun, taken through a coronagraph, which is a special type of telescope which blots out the sun's main disk so that we can see the solar prominences and other disturbances more clearly. How high is that prominence there? About 40,000 kilometers. Here we have superimposed beside the prominence a silhouette of the Earth drawn to scale. This gives you some idea of the sun's immensity. You know that the sun is a star and that the distances between the stars are enormously greater than anything we've talked about yet. After all, compare the brightness of the sun as you can see it in the sky with that of any of the bright stars. And remember that each of those stars is giving off as much or more light than the sun itself does. Immediately you can see that the sun is a very long distance from the nearest of all the stars. How are we going to be able to measure that distance? The Earth itself is so small that it cannot serve as an adequate baseline for any such measurement. So what we do is use the motion of the Earth around the sun during a year to provide a baseline. We make one observation when the Earth is here. We wait 6 months until the Earth is on the other side of the sun over here and make a second observation and come back at the end of a full year and make a third confirming observation. This provides us with a baseline which is 300 million kilometers long. Even that is barely enough for us to be able to measure the distances to some of the nearer of the stars. While astronomers had been attempting to do this for centuries, it was not until 1838 that they were first successful. Now here's the problem. These lights represent distant stars. They're so far away that to get their distance we must make our observations from the two ends of our great solar orbit baseline. We make one observation here, then after 6 months we make a second observation here from the other side of the baseline. Did you notice what happened to the lights as I walked across? Watch with me as I walk back again. See? One of the lights seems to be moving, while the other two are standing still. Now let's have a look at those lights. You can see that none of them really moved, but that this one was closer to you. And as we observed it from the different ends of the Earth's baseline, it seemed to move. The other lights served as a fixed reference pattern against which we could see the motion. If we can measure the amount of the motion, then, knowing the length of the baseline, we can determine the distance to the nearest star. We call this using stellar parallax. The angle involved is very small, enormously less than that in measuring the distance to the moon. In fact, for the nearest star, the angle is just over 1 second of arc. Now, to get some idea of what that is, consider a 25-cent piece whose diameter is exactly 1 inch. Put it 3.5 miles away. Then its diameter will subtend an angle of just 1 second of arc. That seems very small, but the modern astronomer can subdivide that into 100 parts. This means that if the parallax is only 1/100th of a second of arc, the astronomer can measure it and determine the distance to the star. But refined as this method may be, using the stellar parallax, it allows us to get the distances of only a few thousand of the stars in the immediate neighborhood of the sun, astronomically speaking. Now, what sort of a scale are we talking about here? We can send a radio wave from the Earth to the moon and back in just over 2 seconds. It takes light 8 minutes to go from the sun to the Earth. But the nearest star is so far away that light takes over 4 1/3 years to get to us. Over here we have a list of some of the stars whose distances we've been able to measure using the method of parallax. The nearest star is Alpha Centauri at just over 4 light years, and one of the most distant is Rigel at over 500 light years. There's some other stars here whom you will recognize: Sirius at 8 light years, Vega at 23 light years, and Bright Capella at 42 light years. Actually, the distance of about 500 light years to Rigel seems quite a lot, but it's only a very small portion of the total universe and even of our own galaxy. Let's see if we can get some idea more clearly as to the nature of this scale with which we're beginning to work. Light takes just over 8 minutes to come the 150 million kilometers between the Sun and the Earth. Let us represent that distance of 8 light minutes by a block 1 inch long, and see if we can locate the position of the nearest star from which light takes 4 1/3 years to get to the Earth. From here, light would get to the Earth in 1 hour. From here, light would get to the Earth in 3 hours. From here, the light would take 12 hours to get to the Earth. And from way back here, light would take 1 day to get to the Earth. But where is that nearest star from which light takes 4 1/3 years to get to us? To locate it, we would have to go out this way for nearly 5 miles. Now, by the parallactic method, astronomers can measure with accuracy the distances of stars out to 300 light years, and with decreasing accuracy out to about 500 light years. You will remember that Rigel, one of the more distant of the stars that we can measure with parallactic method, is about 500 light years away. On this model, Rigel would be 500 miles away. Now let's take that enormous distance, 1,000 light years across, and shrink it down to a circle only 3 inches in diameter. And consider that within this circle, we have all the stars whose distances we can measure by parallax. Let me put this circle down here. We can represent the solar system as just a mere pinpoint at the center, and our 3-inch circle includes all the stars in the Sun's immediate neighborhood, astronomically speaking. This is our galaxy. As we look out through the great Milky Way, we have the feeling that it has this vast spiral structure to it. In fact, we have many observations that show that it has a structure much like that of many other systems we can see out in space, such as this one in the constellation of Andromeda. Our own galaxy seems to be about 80,000 light years across from one side to the other, and about 10,000 light years thick. Now you can immediately see why the parallax method is not going to help us in getting distances in this vast system of our own, let alone in the great depths of outer space. Clearly, some other way was needed for getting the distances to the more remote stars. One device that has proved exceedingly useful is the photoelectric cell, which we have here. You have probably encountered it in grocery stores where it opened the door for you as you approached. We have wired the cell to a meter with a projection lantern that shows the scale on the screen here so that you can watch the readings. But there's too much light here, so let's get rid of some of that. Now, with the lights dimmed, we have a background reading of 1 unit on the scale. Watch what happens as I take this small test light to various distances from the photo cell. At this distance, I get a reading of just 17 units. If we take away the 1 for the background illumination, we have 16 units of light falling on the photo cell. At twice that distance, here, we have a reading of just about 5. Take away the background reading, and there are only 4 units of light falling on the photocell. That is, as we doubled the distance, we cut the light to only 1/4. Now I will go out to 4 times the original distance, out here, and we have a reading of only 2 units. If we take away the background of 1, there's only 1 unit of light falling on the photocell. That is now, as we have increased the distance 4 times, we have cut the light down to only 1/16 of what it was initially. I believe you can see that the intensity of light varies inversely with the square of the distance. Now I think we're getting somewhere. We have a very sensitive device with which we can measure the brightness of the light, and we have a rule that tells us how the intensity of that light will vary with the distance of the source. Now let's see if we can put that to work. Let's look at the brightnesses of the stars whose distances we can measure easily, that are nearby. Here we have a listing of the order of the brightnesses of some of these stars, and immediately you see that some, like Rigel, are over 500 light years away, and yet are slightly brighter than one like Procyon that's only 10 light years away. This might suggest that the measure of the brightness of the star's light is not going to be a great help to us. But there's more to it than that. The stars are not all of the same color. In the sky are a number that are very dull and reddish, like Betelgeuse in the constellation of Orion. These stars are generally not visible at great distances. But the blue stars, like Sirius and Vega and Rigel and Fomalhaut, Regulus, are quite numerous in the heavens and can be seen at great distances because they're intensely hot and give off an enormous amount of light. Many such blue-white stars are found in the clusters of stars far out in space. And when we carefully examine a cluster of stars, we find that all the blue-white stars within the cluster have very nearly the same brightness. This suggests strongly that all those stars give off just about the same amount of light. If we find another blue-white star someplace and its brightness differs from another such star, we suspect that this is because the two are at different distances and that the brightness has diminished inversely with the square of the distance. This looks like a pretty good idea that we might use in trying to estimate the distances of stars that are quite remote. But before we can use it, we must, of course, check using the distances we have measured by parallax for such stars that are fairly nearby. Here we're going to make a chart on a compressed scale, the light years of distance squeezed together, and the relative brightnesses of the stars on this scale, so that we can see to what extent this idea seems to be confirmed by the observations that astronomers have made. For example, we get from the astronomer observations on the star Vega, whose distance would come right in here, and whose relative brightness would put it right there, and we find that it plots just about there. Both of the pointers in the Big Dipper are blue-white stars, and we can use them because they're not very far away. The brightest of these, called Dubhe, has a distance that puts it there, and a brightness that puts it there. And they have a point just here for Dubhe. The other star of the pointers does not have an ordinary name, but its distance puts it here, and its brightness comes in just here on our scale, and it plots in there, and we'll give it its astronomical name of Beta, the second brightest star in the Big Bear, called Ursa Major. Now let's see how these plot and if they agree with our anticipated inverse square relationship. This looks surprisingly good. Out as far as we can go using a parallaxes, about 300 light years, from these data and many others that astronomers have, we find that this relationship holds very well. We have no check on it out at these greater distances, but possibly we'll be able to use it as a tool. But let's see if it really confirms the inverse square relationship. Here we have a point, star, and if we go out to 10 times the distance, which would be here, the brightness would go down to just 1/100th of what it was at the nearer position. This is just what we would have expected and makes us feel very good that this is a useful tool. Now let's see how we might apply this. Now let's consider another blue star, one so far from the sun that we couldn't possibly get its distance by parallax. Say one out in this direction. We can see that the star is blue, and we can measure its apparent magnitude. From the observatory, we have some readings on that blue star we were talking about. We have a measure of its brightness, which puts it way down here on this scale, at this point. And now let's carry that across to our line. It plots right there. If we take that up to our distance scale, comes in here, for which the distance is 850 light years. I believe by this you can see that if we can measure the distance of some of the blue stars, and we assume that they all give off the same amount of light, we can find the distance of other more distant stars that we can't get at by the method of parallax. Now, astronomers have used the blue stars as a useful tool in probing out into space. They use many different techniques, many instruments, many characteristics of stars. The important thing is that the results are internally consistent. They all agree, and this gives us great faith in the result. It turns out that at the present time, we apparently are able to observe with the biggest telescopes objects so far away that their light takes 2,000 million years to get to us. But you should remember that all these techniques of measurement are fundamentally based upon the time-tested method of triangulation.
In almost everything we do in physics, we are constantly confronted with the need for making measurements. But it is particularly satisfying to be able to see things of sizes normally beyond our reach and to measure them directly. When we measure any length or distance, we do it by reference to a standard so that our measurements will have the same meaning to everyone. If we measure something very large, like the distance to a star, we need large units. and our standard must be scaled up to fit our needs. Now today, we're going in the opposite direction and measuring things that are extremely small. So we're going to have to scale our standard down to fit our needs. Now here is our familiar standard of length in the metric system, the meter. These are centimeters. My finger is just about 1 centimeter wide, or 1/100th of the meter. For something smaller still, like this lead, we can use the millimeter marks. This lead is just about 1 millimeter wide. But if we want to look at something smaller still, like the width of this hair, for example, we find we have no marks to guide us. We need a smaller scale with finer divisions. This little scale is called a stage micrometer. The divisions on this are very small indeed. In fact, there are 100 of them per millimeter. Even with a magnifying glass, we can't see much of these tiny lines. But this scale was made for using with a microscope. Now, the microscope has a combination of lenses in it, so that we get a highly magnified image. We want to look at these lines and compare them with our other scale. Now, when we get this focused, you can see these tiny divisions very well. And we can compare this with a millimeter scale. We can just get 2 millimeter marks into the picture along with the other scale, and you see how many divisions there are. Now let's use the scale to measure that hair. It fits neatly between the two large marks. That is, it covers 10 of the divisions. It's 1/100th of a centimeter wide. Using powers of 10, we say that the hair is 10 to the minus 2 centimeters wide. I have some lycopodium powder here, and I'm going to put some on a microscope slide. I'll blow it on because it's very fine. These tiny particles are the spores of club mosses. Now let's use a different microscope this time, because I want to show you a new kind of measuring device. The scale that you see is the image of a small one in the eyepiece. It's called an ocular scale. To find out what distance each division represents, we can compare this scale directly with the stage micrometer that we saw before. You see that 20 divisions of the ocular scale correspond to 30 divisions of the stage micrometer, or 1 division to 1.5 of the stage micrometer, or 1.5 times 10 to the minus 3 centimeters. This comparison of the scale with the standard scale is called calibration. If we increase magnification, which we do by changing objectives, we must recalibrate. Now, 15 divisions of the ocular scale correspond to 5 of the stage micrometer, or 1 division to 1/3, or 0.33 times 10 to the minus 3 centimeters. Now the lycopodium. This lycopodium spore is about 9 divisions wide. 9 divisions equals 3 times 10 to the minus 3 centimeters. So we've come down to another order of magnitude. Here's some flour, and we can see that the particles are of varying sizes. These have been measured, and the smaller particles are of a size that give us another order of magnitude, farther down the measuring scale. These are about 10 to the minus 4 centimeters wide. To get to the next order of magnitude, we may use specimens of bacteria. A number of these have sizes in the range of 10 to the minus 5 centimeters. This particular specimen is Bacillus cereus. The width is measured at 8 times 10 to the minus 5 centimeters, which is by no means a full factor of 10, but we know there is structure here of the order of 10 to the minus 5 centimeters and smaller. However, we can't see that structure under the light microscope. If we try to magnify one of these pictures, the result reveals nothing more than a larger image of the same indistinct view seen at smaller magnification. So it isn't just magnification that matters, is it? We need more detail. What we need is a thing called resolution. We want 2 points that are very, very close together on an object to look like 2 points, and not like one blurred spot. You see how light plays tricks on us. Now, you've seen that we can't get the kind of resolution that we need just by magnification. The nature of light is responsible for this. Light has certain characteristics that make it impossible to distinguish 2 points that are closer together than about 10 to the minus 5 centimeters. This microscope has as good a resolution as we can possibly get. Money won't buy a way to get better resolution with a light microscope. But we've been talking about light that we can see, visible light. Now, you know that not all radiations are visible, but there are other kinds of radiations that have helped us, and by a large factor. As long ago as the 1870s, it was known that electron streams can cause fluorescent materials to glow. A device like this was developed more than half a century ago. It's called a Crookes tube. It has an electron gun at the small end, and the electrons are propelled across the evacuated tube to cause the face of the tube to glow, just as in a television tube. We can watch it better in the dark. Now, if I put a barrier in the path of the electrons, we can see an important point. The shadow of that cross-shaped barrier is sharp and distinct. This shows that electrons travel in a straight line. Much later, it was learned that electrons can be controlled and focused, and this new knowledge led to the development of a new kind of microscope using electrons instead of light, an electron microscope. We have our camera in the laboratory at MIT, and Dr. Alan Hodge is demonstrating one of the electron microscopes used in his research. Like the Crookes tube, the electron microscope also employs an electron gun, an evacuated tube into which the specimen is inserted, and a fluorescent screen. Because the tube is evacuated, we cannot, of course, look at living specimens. When the electrons are accelerated by a high voltage, they pass through the specimen, more electrons going through thin spaces than through heavier portions, and are focused to give us a highly magnified shadow picture on the fluorescent screen. Electron microscopes are in use at many laboratories, and we've gone to Professor Chapman at Harvard for this electron micrograph of our friend, the Bacillus cereus. Not only is this magnification more than 100 times greater than we obtained under the light microscope, but we get resolution, which allows us to see detail clearly. Unlike the picture made with visible light, which gives us only the outlines, the electron micrograph provides a view of structure. We can see where the cell has divided and distinguish the completed cell wall at the division. With resolution like this, we can even see virus particles. It's easy to realize how valuable a tool the electron microscope has been in medical and biological research. Dr. Robley Williams of the University of California has provided us with these micrographs. The tobacco mosaic viruses here have a width of 1.5 times 10 to the minus 6 centimeters, which gives us a measurement in our next smaller order of magnitude. To help us reach the next order, Dr. Hodge is preparing a crystal specimen. A device called a microtome is used, a slicing machine which cuts off minute wafers of matter. They are so small that they can't be seen except by the flashes of light they reflect. As they float on water in the container, they can be picked up and prepared as specimens for viewing. This is an edge-on view of a platinum phthalocyanine crystal. The lines show the spacing of the molecules, which are only an atom in thickness. Those stripes are only about 10 to the minus 7 centimeters apart. Now, when we see separate layers of molecules, we're really getting to small things. After all, a molecule is the smallest bit of a substance that still retains the identity of that substance. But molecules are made of atoms. Can we see atoms? we can calculate the average distance between atoms in a metal. And it turns out that this distance is less than a factor of 10 below the distance that we've been seeing between molecular layers. But when we come this close to seeing atoms, we find that we're reaching another limit of resolution. This is as far as we can go with electron beams. Another difficulty is that separate atoms don't cast very good shadows, so that shadow pictures, like the ones we've been seeing, don't show us very much. We need more contrast. A new idea to help us farther down the scale of seeing came from Professor Irwin Miller of Penn State University. We'll take you to his laboratory and let him show you.
If you compare the smallness of an optical microscope with the large dimensions of an electron microscope, you might think that a better microscope will be much larger, but actually this needs not to be at all. We have here a new microscope, a so-called field electron microscope, which consists, as you see, of a very small tube and which contains all the essential parts. To show you how it looks inside, I make a little sketch. We have a glass vessel which is evacuated, and I am sketching it here. This vessel has sealed in a fine metal tip which stands opposite to a fluorescent screen, just a fluorescent screen in a television tube, for instance. And now if we put high voltage to this thing, we get electrons streaming out from that needle and projecting an image onto that screen. Now, if you want to know how much magnification you get with this, I should explain it to you in a second sketch. Now imagine the tip is very highly enlarged. We have here, in fact, the very end of that needle, which has a very perfectly rounded tip. And from this end, electrons stream out, always normal to the surface, and they stream to the very distant fluorescent screen, which I simply sketch here. And now the magnification, capital M, is determined by the distance from the tip center to the screen, which I call R, and the ratio of this distance to the tip radius, which I call small r. And now we have a tip radius, let's say, of 5 centimeters, and a screen radius, a screen distance of 5 centimeters, and the tip radius is only 10 to the minus 6 centimeters, which is very small. You cannot measure it directly, and this gives a magnification of 500,000 diameters.
From Dr. Miller's film records, let's first compare the thin needle under a light microscope with the point of an ordinary pin, which looms like the nose of a rocket. Actually, the tip of the fine needle cannot be seen. The picture shows only the larger midsection. Now, in this picture, taken with an electron microscope, the tip is not only visible, but large enough for us to measure. Since the magnification is known, it's easy to calculate the actual radius. You'll remember that the needle is sealed into the tube, pointed toward the face of the tube. As the voltage is applied, electrons stream out. The screen begins to glow, and a pattern appears. The screen is bright where many electrons hit. This pattern is symmetrical, because the tip has a regular crystalline structure. Although the lateral resolution is no better than that of the electron microscope, we get improved contrast, because the electrons come directly from the tip surface. Now suppose we add something to the tip surface, such as a few phthalocyanine molecules. This is a model of one, in which each ball represents an atom. The structure is well known. The molecule is thin and flat, only one atom thick, and you can note the fourfold symmetry of the face. When some of these are added to the tip surface, the molecules appear and disappear as they turn, and the four-leaf clover appearance is noticeable. When the temperature of the tip is raised, they quickly boil away. Now we see molecules, groups of atoms, but not individual atoms. At this point, the field emission microscope is at its theoretical limit of resolution. So Dr. Dr. Miller went a step further, seeking better resolution. He gave up using electrons and developed the field ion microscope using positive ions instead, repelled from a positive needle. A positive ion is an atom from which an electron has been stripped. Now, ions cannot be pulled from the needle tip as electrons were, so they must be introduced in some other way. Helium atoms are fired against the tip, lose their electrons, thus becoming positive ions, and are repelled in straight lines to form an image on the screen. In this new device, the needle tip is mounted in a separate structure, and the tube is operated vertically. The pictures enable Dr. Miller to study the arrangement of atoms in crystals and permit him to record changes that occur when materials are added or taken away. We are looking at atoms. The bright spots are individual atoms in a platinum crystal. The symmetry here illustrates the regularity that exists even in such minute pieces of matter. The image of each atom we see is formed by at least 10,000 helium ions reaching the screen per second. Here's a picture formed by a tungsten needle, showing the regular crystalline structure of tungsten. Since it is known that the atoms in tungsten are arranged in cubes, like this, Dr. Miller has been able to construct this model of the whole tungsten needle tip, using cork balls for atoms. The field strength is greatest at the edges of these flat faces, and the helium ions that come from these atoms are the ones that make the picture. At low temperatures, the atomic surfaces of the tip appear immobile. But if we raise the temperature, the image on the screen comes to life. These pictures are composed of a series of still photographs. They are, of course, time-lapse photographs, so that what we see is not the true speed of the reaction. Surface atoms on the needle are torn off, first from the tip, then back along the planes and layers. For the first time, we can see and study reactions between atoms. By measuring the distance between atoms on the image and using the known magnification, we find that the atomic spacing agrees with previous theoretical calculations. These distances are of the order of 10 to the minus 8 centimeters. We have come far down the scale of measurement that we began with the standard meter stick. This last range of distance has been so recently reached that few, even in the scientific world, have seen it.
You are listening to the beat of my heart. If you timed your heart, you'd find that it beats about once every second. But the motion of the heart is not completely regular. It is not exactly the same from one beat to the next. Here's a graph of a heart beating, an electrocardiogram. You can see from this that the heart's motion is complicated. But it does repeat itself, but not exactly. The time, for instance, for these two beats is not identical. In this film, we're going to talk about motions which do repeat themselves exactly, motions which are periodic. Here's a graph of a periodic motion. Periodic motions, no matter how complicated, can be analyzed in terms of a particular kind of periodic motion, which is called simple harmonic motion. More than this, simple harmonic motion itself occurs frequently in nature. So an understanding of this type of motion is important.
I'm going to show you a few examples of periodic motion. This ball is suspended by a very long spring. Its period of vibration is about 4 seconds, so that its frequency of vibration is about 1/4 of a cycle per second. Over here, there's an inertial balance. It vibrates with a period of about 1 second. This tuning fork vibrates much more quickly. I can't tell by eye here what the period is, but it says on the fork that it makes 440 vibrations per second, and therefore its period must be 1/440th of a second. The period of this bouncing ball is about 1/2 a second. But as you can see, the period keeps on decreasing, and therefore this isn't a good example of periodic motion. Over here, there is a periodic motion which you have already studied. The motion of this ball repeats itself exactly with a period of 5 seconds. This is uniform circular motion. You know how to describe this motion completely. You can actually write down equations which describe this motion. But what about the other periodic motions that I have shown you? Can you write down equations which describe them?
This spot is moving with the particular kind of motion that is called simple harmonic motion. How can I describe this motion? Well, to describe any motion completely, I just have to know how the displacement changes with time. And this apparatus is arranged so that the pen attached to the moving spot will plot a displacement time graph. This glass plate is movable, and I'm going to set it moving in this direction with a constant velocity. The distance that it travels in this direction will be proportional to the time of travel. The pen will be moving up and down in simple harmonic motion, but in each instant of time, the glass plate will move along in this direction a fixed distance. The trace that the pen makes will be a displacement time graph of simple harmonic motion. Now I'm going to set the plate moving.
Very nice. You're sure this is simple harmonic motion?
Oh, I guarantee it.
I have it on good authority that this is a displacement time graph for simple harmonic motion. Now I'm going to use this graph to find out how to write an equation which describes simple harmonic motion. I drew axes on here earlier, a vertical axis and a horizontal axis. The pen first touched the plate up here, so time is plotted in this direction. Displacement is plotted in this direction, displacement x. And I've chosen the zero of displacement so that the maximum displacement this way is the same as the maximum displacement this way. I'll call the upward direction positive, the downward direction negative. Now you know how to find velocity from a displacement time graph. The slope of this graph at any point gives the velocity at that point. So down here, I'm going to plot a velocity time graph. I've put in these vertical lines to help me. They are spaced 1/4 period apart. Remember, this much is one period, then the motion starts over again. To start with, the tangent is horizontal. The slope is 0, so the velocity is 0. This, of course, is where the spot in simple harmonic motion stopped and started in the other direction. Then, a quarter period later, here, the tangent is steepest, and the slope is negative. I haven't specified what the scale of velocity is here, but I will suppose that the magnitude of the slope, that is the velocity, is this much. Then another quarter period, the slope, the velocity, is 0 again. Another quarter period, and the slope is now positive. I think you can see from the symmetry of this graph that the magnitude of the slope here is the same as the magnitude of the slope here. But here, the velocity is positive. Then another quarter period, the slope is 0 again, and I have come one full period. Then the motion repeats itself. Of course, I can't join these points with straight lines because the velocity is changing continuously here. I could plot more points in between. If I did make these measurements, I'd find a curve that looked something like this. This is the velocity time graph for simple harmonic motion. I think you can see that it has the same shape as the displacement time graph, but the velocity graph is displaced this way one quarter period. When the displacement is a maximum, the velocity is 0. When the displacement is 0, the velocity is a maximum downward or upward. The spot in simple harmonic motion is moving fastest at the center of the motion. Now, what can I find out from this graph? The slope of a velocity time graph at any point gives the acceleration at that point. So down here, I'm going to plot an acceleration time graph. I could do this, as I did before, by taking slopes here, but this time I don't have to. This graph is the same shape as this graph, so that when I take slopes from this graph, I'll just get another graph of the same shape, but displaced another quarter period. It will look something like this. It's difficult to do a good job of these graphs without actually measuring a slope at a large number of points. These, of course, are just rough sketches. But I did do this carefully before. These are the graphs that I obtained. The scale that I've used to plot acceleration is arbitrary. It's arbitrary for each of these graphs. But I have chosen the acceleration scale so that the size of the acceleration graph is exactly the same as the size of the displacement graph. And now I can show you what I mean when I say that these graphs have the same shape but are shifted. They do have the same shape. The fact that these graphs have the same shape but shifted one quarter period is characteristic of just one kind of periodic motion. Any periodic motion that behaves in this way is simple harmonic motion. Each of these graphs describes simple harmonic motion, but I want a mathematical relation to describe simple harmonic motion. How can I find this? I want you to compare the acceleration graph and the displacement graph. When the displacement is a maximum, the acceleration is a maximum too, but in the opposite direction. As the displacement decreases, the acceleration in magnitude decreases. They both become 0 together. The magnitude of the acceleration is always proportional to displacement, but the acceleration is always in the opposite direction to displacement. How can I express this mathematically? Like this. Acceleration is proportional to the negative of displacement. This mathematical relation defines simple harmonic motion. Now what about force? All of this has just been the kinematics of simple harmonic motion. What about the dynamics of simple harmonic motion? Whenever a mass is moving with this kind of motion, what sort of force must be acting on the mass? Well, whenever an unbalanced force acts on a mass, according to Newton's law, the force is proportional to the acceleration. Now I want you to compare these two expressions. I think you can see that whenever a mass is in simple harmonic motion, there must be an unbalanced force on it which is proportional to the negative of displacement. F is proportional to minus x. Now I'm going to write this expression as an equation. I can do this by introducing a proportionality constant, K. This is called the force constant for the particular simple harmonic motion. Whenever a force behaves in this way, there must be simple harmonic motion. Now, Dr. Hume has an experiment set up so that we can measure some forces.
This is periodic motion. Is it simple harmonic motion?
This is the equilibrium position of this puck. If it's displaced away from me, the springs exert a force on it towards me. If the puck is displaced towards me, the springs exert a force on it away from me. The springs exert a restoring force on the puck, and a restoring force is necessary for simple harmonic motion. But as I showed you, for simple harmonic motion, the restoring force must be proportional to the displacement. And to see whether it is here, we'll have to make some measurements. The scale will show the displacement of the puck in centimeters.
This is a spring balance, and it's calibrated in newtons. I'm going to hook it onto the puck and pull the puck away from its equilibrium position and measure the force. It's now at the 10 centimeter mark, and the force is 1.1 newtons.
1.1.
20 centimeters, 2.2 newtons.
2.2.
30 centimeters, 3.4 newtons.
3.4.
40 centimeters, 4.6 newtons.
4.6. You can see that here the restoring force is proportional to the displacement. This means that this motion must be simple harmonic motion. If we plotted a displacement time graph for this motion, it would look exactly like the displacement time graph that we plotted before. Now, what about the period of this motion? What would you expect the period to depend on? Dr. Hume has been putting a lead ring on the puck. Would you expect the period of this motion to be larger or smaller than before? I think you can guess that with a larger mass, more inertia, the motion is more sluggish. The period is larger than it was before. It's still simple harmonic motion, but of a different period. Suppose that I used a stiffer spring here. What would that do to the period? Well, when the puck is displaced, the restoring force on it would be larger, the motion would be quicker, the period would be less. But just how does the period depend on these quantities? We'll have another look at the equation. So far, I don't have an equation for acceleration, but I can derive one. Force is equal to this, but always, as I said before, by Newton's law, unbalanced force is equal to mass times acceleration. And I want you to compare these two expressions for force. Equating these, acceleration is equal to minus k over m times displacement. This equation, just like this expression, defines simple harmonic motion. But in neither one of these expressions can you see the period, the thing that's easiest to measure. It turns out that it is possible, by mathematical means, to derive an expression for the period from this equation. But the mathematics is mathematics you probably haven't studied yet, so we're going to have to get at the period another way. We are going to do it by using what you already know about another kind of motion, uniform circular motion.
You can see that there's a connection between uniform circular motion and simple harmonic motion. Now I'm going to ask you to use your knowledge of this motion to analyze simple harmonic motion. Usually, we work the other way around and find out about motion in a curved path by analyzing it into its component motions in straight lines. I'll show you what I mean. Here's a model of a ball shot horizontally. The model shows the position of the ball at equal intervals of time. You know that you can calculate this motion by thinking of two independent motions. One in this direction, the horizontal component, and one in this direction, the vertical component. Now look at the model from another direction. It looks like a ball falling straight down with constant acceleration, the acceleration due to gravity. You are seeing the vertical component of the motion. Now I'll turn the model so that you can look down from above. It looks like a ball moving with constant velocity. You are seeing the horizontal component of the motion. This curved motion can be analyzed into these two independent components. You can think of circular motion as having a horizontal component and a vertical component. When I turn this sideways, you see the vertical component of the motion. The spot appears to move up and down in a line, and it looks like simple harmonic motion. Let's investigate. I'm going to put some vectors on this circle one at a time, and they will represent the displacement, the velocity, and the acceleration of the spot moving in uniform circular motion. And when you look sideways at these vectors, they will represent the displacement, the velocity, and the acceleration of the vertical component of circular motion. First, the displacement. The magnitude of the displacement vector is equal to r, the radius of the circle, and it points from the center out to the moving spot. Now watch the vertical component of the displacement vector. Now it's 0. Now it's positive. Now it's 0. Now it's negative. You are seeing the displacement vector that Dr. Ivy has called x. It points from the 0 position out to the moving spot. Now the velocity. This stick will represent the velocity vector. Remember that the velocity is always tangent to the circle, and that it remains constant in magnitude as the spot moves around. Now watch the vertical component of the velocity vector. Now it's 0. Now it's a maximum. Now it's 0 again. It's a maximum at the center of the motion, and 0 at the ends. This is the way the velocity varies in simple harmonic motion. What about acceleration? I'll take off the velocity vector now. This will represent the acceleration. The acceleration of the spot moving in the circle is constant in magnitude. And it points towards the center of the circle. Now watch the vertical component of the acceleration. Now it's 0. Now it's a maximum. Now it's 0. Now it's a maximum. When the displacement is 0, the acceleration is 0. When the displacement is a maximum, the acceleration is a maximum. When the displacement is downward, the acceleration is upward. And when the displacement is upward, the acceleration is downward. Now, to help you to see that the acceleration is proportional to the displacement, I'm going to repeat this. I can make this acceleration vector to any scale that I want. So I'm going to use one which is exactly equal in length to the displacement vector. Now you see it as equal to the displacement x, but pointing in the opposite direction. The acceleration is exactly proportional to the displacement, but in the opposite direction. This vertical component of uniform circular motion fits exactly the definition of simple harmonic motion. A is proportional to minus x. In fact, we use circular motion to produce the simple harmonic motion that you saw before. The pen moves up and down in such a way that it always has the vertical component of the motion of the spot which moves uniformly in the circle. The reason for looking at circular motion was to find an expression for the period of simple harmonic motion. The period of this simple harmonic motion is the same as the period of this circular motion. The length of this acceleration vector is equal to r, the radius of the circle. I chose the scale to make it this way. But you know that in fact this acceleration is equal to 4 pi squared over t squared times r. This is the scale factor, and t is the period. And the whole thing is the centripetal acceleration. Now, with this same scaling, you saw the vertical component of acceleration as equal in length to the displacement x. Now, the same scale factor must apply. This is the magnitude of the acceleration in simple harmonic motion. The acceleration is in the opposite direction to the displacement, so the vector A is equal to minus 4 pi squared over t squared times the vector x. Now I'm going to compare this expression for acceleration with the one that Dr. Ivy had. These are both expressions relating acceleration and displacement in simple harmonic motion, so they must be equivalent. My expression is based on kinematics. I derived it using your knowledge of circular motion. So mass and force are not involved. Dr. Ivy introduced Newton's law, dynamics. So in his expression, mass and force constant appear. Now I'm going to compare these two expressions, and you can see that K over M must be equal to 4 pi squared over T squared. This means that T squared is equal to 4 pi squared M over K. Now I have to take the square root. T is equal to 2 pi into the root of M over K. Finally, we have it, an expression for the period T. The period of a mass M moving in simple harmonic motion under the influence of a restoring force whose force constant is K.
Now you know how the period depends on mass and force constant. As I suggested before, by intuition, for a larger mass, the period is larger. The motion is more sluggish. For a stiffer spring, the period is less. The motion is quicker. I've been doing some calculations for this particular simple harmonic motion of this puck. First of all, from the data that we had before, I calculated the force constant, K. A force of 4.6 newtons gave a deflection of 40 centimeters, or 0.4 meters, so that the spring constant, or force constant, is 11.5 newtons per meter. And I used that in here for force constant. I weighed the puck. Its mass was 3.67 kilograms. Then I did the arithmetic, and the period came out to be 3.54 seconds. Now I'm going to measure the period and see if this is what I get. Zero. 1. 2. 3. 4. 5. 18 seconds. So the period is 3.6 seconds, which, as closely as experimental error will allow, is equal to 3.54 seconds. So we get the same value calculated as experimentally as we must do. We have done the theory of simple harmonic motion.
Here is a periodic motion that's very familiar. Simple harmonic motion. Remember, whenever simple harmonic motion occurs, there must be a restoring force proportional to the displacement. Here, there is a restoring force, all right. And this arises because of gravity. But is the restoring force proportional to the displacement? Well, for small vibrations of a pendulum, it is. So the motion of a pendulum with small vibrations is simple harmonic motion. The larger the vibrations, the less true this is. The period in simple harmonic motion depends on the mass vibrating and the force constant of the system. Watch what happens here when we double the mass.
Double the mass?
Yeah, well, more or less.
If you timed us now, you would find that the period is exactly the same as it was before I got on. The period here is independent of the mass. And this is because I have changed the force constant, too. The force constant here depends on the force of gravity on us. That is, on our weight. And when I increase the mass, I also increase the weight in proportion. The period of a pendulum does not depend on the mass vibrating, but it does depend on the length of the pendulum.